Welcome you all to a new session. This is the last topic of our Unit 3, where we are going to see the Verilog codes for different gates and the circuits which we are going to design using Verilog is the combinational circuits. Under combination circuits, you are going to see all the basic gates like encoder, decoder, multiplexer, full adder, off adder, full subtractor, off subtractor. So those kind of things you are going to observe clearly here. Now let us start with basic gates first. You know the basic gates AND, OR, NOT, NAND, NOR, and XOR and exclusive NOR. So we are going to see those kind of things here now currently. Now Verilog code. Verilog code is we call it as a HDL code. HDL stands for hardware description language. Means I am going to describe a hardware using a language. That languages are of two types. One is Verilog. The other one is VHDL. So we got two languages to describe a hardware language. Now VHDL stands for VLSI HDL. That is very large scale system integration hardware description language. So now currently we are going to study about Verilog. Now under Verilog, my first program is related to my basic gates. Now my basic gates, you know, I have AND gate, I have OR gate, I have NOT gate, I have some universal gates like NAND, NOR, and we have special purpose gates like XOR and XNOR. So these are the gates which are basically present here, using which we are going to learn about the designs under Verilog form. Now let us see. Now this is a program which is going to define all these gates. This is a module. I am defining a module which represents logic gates. That means all logic gates. I am considering all these logic gates for two inputs. So my two inputs I am declaring it as A comma B. So for two inputs, all these outputs are to be generated. Now how many are there outputs? 1, 2, 3, 4, 5, 6 and 7. So I am considering Y1 to Y7 as my outputs. A and B as my inputs, Y1 to Y7 as my outputs. So I am declaring my input variables as A comma B, and for my output I am declaring Y1 to Y7 here. Now AND gate. My code is I am having a keywords like AND, OR, NOT, NAND, NOR, XOR, XNOR. So these are my keywords which are already present in my Verilog tool. So I am declaring AND operation which is going to generate Y1 output for input variables A comma B. Similarly, OR operation which is going to generate a Y2 value as output for input values A comma B. NOT operation, Y3 is going to give you a output value for input value of A. Now NAND operation is going to generate Y4 output for input variables A comma B. NOR operation is going to generate a Y5 output with the input variables A comma B. Next XOR, which is going to have output as Y6 and input variables as A comma B. Last XNOR operation, which is going to give me Y7 as my output, A comma B as input variables, and this is my ending statement for my program, right? So I am beginning with a module, I am ending with a module. In between it, I am just declaring my input and output variables. For that, I am declaring what function it has to perform: AND operation, OR operation, NOT operation, NOR operation, XOR, XNOR. So these are my operations. Now I declared my functionalities which need to be performed along with input and output variables. Now I need to give some values which I need to assign to it. So I am going to write a test bench here. Means I am going to test this particular code whether it is working properly or not. Let's see it. Let's observe the test bench here. So this is our test bench. This is my test bench. Now, see, I am declaring here my module, that is module test bench with inputs I am mentioning it as register A and register B. Means I need two registers where I can store value of A and value of B. So I am taking two registers here. And with the outputs I am having wires. So while writing a test bench, you need to declare your input variables as registers always, and you need to declare outputs as always wires under Verilog code. Now I declared my input variables as A and B as registers, and outputs as y1, y2, y3, y4, y5, y6, y7 as my wires. So this is what the declaration part under test bench. Now after that I need to initiate my particular design. So that's the reason I call it as initiate the unit under test. That is UUT means unit under test. I am going to test my module. So that what is the test? The test which I need to perform for my logic gates. So the logic gates UUT, I am mentioning my dot A of A, B of B, Y1 of Y1, Y2 of Y2, Y3 of Y3, Y4 of Y5, Y5 of Y5, Y6 of Y6, Y7 of Y7. I am ending my module. Means I am initiating my input variables along with my output variables. So A and B is getting also initiated, and my output variables are also getting initiated, that is y1 to y7. Now once initiation is done, then I need to initialize my inputs also. See, initializing my inputs, then I need to check my version also, like I need to check my input variables. Now you can see A is equal to 0 and B is equal to 0 as two values. Now I cannot have only two values, or I cannot have only 0 0 value for testing my gate. For two variables I will be having four input combinations, that is 0 0, 0 1, 1 0 and 1 1. So for initially I am taking it as a 0 0, and this 0 0 should be there should last for 100 nanoseconds. Means it is waiting, I am giving the delay for the two outputs or two input variables to be at the value at 0 0 at for 100 seconds of time. Now once 0 0 combination is completed, I need to repeat the value, that is A is equal to 1 and B is equal to 0. So what happens? Again my variables after 100 seconds it is going to change its value to 1, 0. So for these two combinations it is going to generate the output value. Similarly, if I want to give 0 1, again I need to give a delay of 100 seconds so that I can change my variable values from 1 0 to 0 1. And if again I wanted to give one more input variable as 1 1, then I can give again 100 seconds of delay where I can generate A is equal to 1, B is equal to 1 input variations for output variables for all the logic gates of AND, OR, NOT, NAND, NOR, XOR, XNOR, and whatever the gates which we have declared at the program level. Now let's get on to this. This is what the programming and the test bench which we need to represent for any kind of logic gates. Now similarly, if I am taking a off adder circuit, now you know off adder circuit clearly. Now this is my off adder circuit, off adder program. Now let's draw a diagram so that you will understand the thing. Off adder, you know, I am having a exclusive OR operation between A and B, which is going to generate me sum, and if I need my carry to be generated, which is AND operation between my input variables A and B. So this is generating my sum value, this is generating my carry value. For this diagram I need to write my program. Now you see I have declared my module off adder. Off adder is the module name, and I am declaring my inputs and outputs, that is A comma B as my input variables and sum and carry as my output variables. Now input variables A comma B, and I am declaring output variables sum and carry, means I am defining them. Already I have declared at module level, I am defining them individually, what are my inputs and what are my outputs. After that I need to perform XOR operation, means I need to perform this XOR operation to get my sum. So that's the reason you can see XOR is giving me sum as my output, A comma B as my input values. And AND operation, this is my AND operation. This AND operation is giving me carry. So AND of carry means output comma input, that is carry comma A comma B. And I am ending my module. So this is what related to the off adder circuit. And after this we will see the test bench. Why? Because the test bench is the area where we need to provide some input combinations to my design. Let's see that. This is a test bench. Now test bench you can observe clearly. I told you that inputs are to be declared using registers and outputs are to be declared using bytes. Now you can see clearly module, test module, inputs I am declaring as registers and outputs I am declaring it as bytes, sum and carry. Then I am initiating my design, initiating the design where I am declaring my inputs and outputs, and initial begin I am providing my first value as 0 0 and I am providing a delay of 100 seconds. Then I am providing a next value as 1 0 and again I need to provide the delay. The delay you can see 100 seconds I have provided after that. Then again I am ending my module. Once if I am ending the module, then my test bench is completed. Now how to run this program and how to way to check means we are having a separate tool called model sim or Xilinx tool where we are going to implement this design as well as test bench on that particular tool, and we can check our results after simulation whether my gates are working properly or not, whether it is giving me the required answer or not. We are going to check over there. Similar, but the practical nature of how they are working, whether the simulator is producing the proper simulation result or not, those kind of practicality will not be available for our classwork. But for exam sake, we need to write these programs. No need of studying of test bench also, but writing a program is very, very important for us here. Next, coming to the next program, that is full adder circuit. Now you know the full adder circuit. Full adder circuit means I need to add 3 bit of information. Means adding 3 bit of information means the full addition should be done. Means I need to add A, B and C in. Means a carry in should be also provided for that particular. Means I am going to have 3 inputs with an XOR operation, that is A, B, C in exclusive OR giving me some value, and AB, BC and CA. 3 AND gates given to 1 OR gate producing me output as carry. Right? Now this thing should implement onto a hardware now. Means I need to declare these input variables along with my output variables. Now see here, we will do one thing. Now see here, I am declaring my module as adder, where I am declaring my input variables as A, B, C in and output variables as sum out. And same thing I am defining here. A input of 3:0 means A is of 3:0 means A got A of 0 value, A of 1 value, A of 2 value, right? Now similarly B got B of 0, B of 1, B of 2 value. Means A and B are of 3 bit in nature. 3 bits in nature. Next I am declaring my C in. Then my output values, you can consider my output value is sum. Means I need to generate sum of A plus B, right? Sum of A plus B means it should have S of 0, S of 1, S of 2. Right? Similarly, C out will be only one variable. If I am able to generate a carry from my last MSB bits, that carry will be stored onto C out. Now, full adder operation. Now you can see clearly I am declaring my full adder FA1. FA1 I am declaring A of 0 and B of 0. And next A of 0, B of 0 after declaring I need to get the value of sum of 0, C in and C out 1. Means initially my C in I am considering this value including with A of 0, B of 0 and C in. Now this sum 0 is going to produce C out 1, which need to be passed on to the next higher order bit. Means it is a 3-stage full adder operation. 3-stage full adder option. Full adder 3, full adder 2, full adder 1. Now I am providing here C in and A, B, C. Now here what happens? A of 0, B of 0. Now this is A of 1, B of 1. This is A of 2, B of 2. Means when I am generating sum here, this carry need to be propagated here. Then again after generating sum here, it should propagate one more carry here. So that kind of operation need to be performed. So this is what the structure it is going to define. And this is how we write the programming for any kind of Verilog. So this is the same thing which we are going to implement for other modules also. Okay, thank you one and all. You can look after the other designs also in the same PDF.